I'm Zach, and I've been working on the Crostini project for about a year and a half now. This project has been known by a few names over the past, including maybe Chrome OS VMs or Linux for Chromebooks. The idea of the project is the same, basically to expand the kinds of apps users can run on their Chromebook without compromising security. So I'd first like to talk about some of the history of the project. A couple of years ago, we had the idea of adding Android apps to Chromebooks. And this was great. This was, allowed us to meet a lot more of our users' needs. And we did this using a containerized approach. We thought after releasing this that maybe we could go one step further. Maybe not just Android applications, but other kinds of applications as well. And maybe even improve the security story for those kinds of applications using yet another layer rather than just containers. So to help drive this development, we thought about what kinds of applications would be useful and make sense for a Chromebook type device. And going along with the theme of Arc++, we thought the tools used for Android developers. This dovetailed quite well with the idea that we wanted developers to actually focus on making sure their Android apps worked well on Chromebooks. So we thought Android Studio, ADB, Fastfood, these are obvious choices. It wasn't until later that we had the idea that we should be using VMs rather than just containers. But we kind of realized this when we present developers with any kind of tool, they'd be able to attack the same kinds of services that Arc++ apps could. And that's when we decided we have to use VMs plus containers. Of course, then we got to thinking, well, how are we actually going to run these applications inside of a VM? Are we going to use a already existing tool like QEMU or VirtualBox being famous examples? Are we going to use something developed internally? There's a few of them that exist. But we kind of we always ran into the same problems we did, which is security. All these code bases are giant chunks of C code. They don't always do what we need them to do, and it seems like on a pretty regular basis there are vulnerabilities and bugs found for them. And that's, once we tackle these technical issues, we then run to another one, which is distribution. For Linux applications or applications in general, there's a myriad of choices, new and old. For developers, they kind of have each one of them, they're kind of used to their own way of doing things. And on top of that, would we target people other than developers? As it turns out, it's very hard on a Chromebook to target other kinds of users. Like the kinds of users that we already have on Chromebooks are well supported. The kind of people who are okay with using just a browser. But for other people like, say, artists or other creative types or gamers are a little bit more difficult. Gamers in particular demand pretty intensive hardware, and we simply don't have that kind of thing on Chromebooks, not today at least. And artists like to use things like peripherals and software that isn't well supported on Linux anyways. And so those sort of weren't really our goals initially with the project. And that's kind of how we ended up with what we have today, which is Crostini, designed to run Linux apps with a focus on developers. Hopefully more in the future, though. All right, so just a quick idea of what the product we're actually presenting as it exists today. It's kind of, you can run it in two different forms. One is sort of the lower level way, and the one is the way that we're working on, and it mostly works, but isn't quite yet complete. So in any Chromebook that you have today, you have the Chrome OS shell, or crush. You can open it with Control-Alt-T. And if the Chromebook you're running happens to be one where we currently have Crostini on, and you're in dev channel, not dev mode, you could run that first command there. The Penguin name is just a name. It could be anything. But the idea here is it starts a VM. Now, this VM that is started is not actually that useful. It's based off of Chrome OS, but very minimal. It's completely read-only, and its only use is essentially to configure the network and allow you to run containers. I'll get into why we run a container more in a bit. And once you're in this VM, you can run, we have a couple scripts dealt with it, but basically it's using LXC to download or start a container. In this case, we call it, that's not a typo, it's called Termina. I'll get into more of that name later, but that's also like Penguin, mostly arbitrary.
You got those two names switched?
No, the first one was Penguin. Sorry. This one here and this one here.
Yeah.
Yeah, no, that's correct. Anyways, so this is all rather low level, and what we're kind of developing today is a UI for people to do this. To automate starting a VM and starting a container for you with all the default settings to make things pretty easy. And then once you're in there, you're presented with a terminal that's basically a full Debian environment. You could do what you've done before in Debian, install packages, run applications, including GUI applications. And we find that this sort of free approach is most useful to the most number of developers out there who enjoy a Linux environment. Now, there's actually kind of a lot going on there. Even in that simplified overview, there's a whole host of applications and daemons and pieces of software that we wrote to make it all work. And I wanted to devote this presentation to the more technical side of how these things work. So, as a quick overview of what's going on behind the scenes when a user clicks an icon in Crostini or in the Chrome OS launcher for an application that's in Crostini, we have these 10 steps. So simple. Now, before I get into this, I just want a quick disclaimer that a lot of our projects are named after French words, and I'm going to butcher them. And that's traditional. That's actually how we pronounce them in the team. So please forgive me. So user clicks on an icon. This is handled by Chrome. Chrome handles all of the UI in Chrome OS. And the way Chrome launches, so let's say this is a fresh boot. So there's not any VMs already running. There's no containers running. They've already been installed. There's already applications, but they haven't actually been brought up. So Chrome will use debug-d to start Concierge. What Concierge is sort of a manager for all of the VMs in the system. And if there hasn't already been one started, it will start CrossVM with the user's data in it for that particular VM. And then that VM will boot a Termina image, which is that simplified Chrome OS image that is only designed to be read-only and start other containers. And inside of there, the init process, which is called maitre-d, or mate-read, as I've habitually started calling it, will then bring up the network, and it will tell Concierge, oh, we're all good here, things started up successfully. And then Concierge will tell maitre-d to start the actual container. That's that LXC command I showed you from a couple of slides ago. Oops. So once that happens, the actual the environment is ready to go, but no application is actually started yet. And to do that, we have yet another daemon that's running inside of the container. Maitre-d was running inside of the rootfs, but now we've got the container with the full environment. We've got Garçon, or Garcon, as you will probably hear me slip in and out of saying, depending on my habit. That is a daemon that will then actually start the application. So you've got an application going. Let's say it's it's an application that user actually wants to see. The way we accomplish that in a well-integrated fashion on Chrome OS is using a pair of packages called Smallier or Smallyar and Verda Wayland. You can see which one I named, the easier to pronounce one. So what these do, what Smallier does is it sort of, well, I'll get into that more later, actually. I've got a slide for it. But it runs inside of the container and will help smooth over some issues. And Verda Wayland will actually pipe the Wayland protocol out of the guest into the host, where Chrome will handle it. Chrome actually has a Wayland server running in it, that composites all sorts of windows. This is actually the same thing Arc++ uses to show all of its windows. This gives us a well-integrated environment. Users shouldn't be able to tell the difference between a Chrome window or an Arc++ window or a Concierge or a Crostini window. And then from there, Chrome shows the window, handles all the input, and things work more or less how you expect. So that was the sort of really high-level view of things. Let me go into a little more detail about lots of these pieces. Probably the one I'm most familiar with, but perhaps least visible part, is CrossVM. This is sort of equivalent to QEMU or VirtualBox in that it's running a virtual machine on Linux. However, like every other virtual machine on Linux, it's using KVM under the hood. So the host Linux kernel is actually handling running the VM in a hardware accelerated fashion. CrossVM just implements the para-virtualized devices, which I have enumerated in the slide. We have only a few of them, but it turns out that's more than enough to get things done. One unique thing about CrossVM, though, one of the reasons we actually decided to write it ourselves, is that, like Chrome, it subscribes to a sandboxing model. Each device is running in a separate, isolated process. This is important, of course, because devices are what is exposed to our guests, which we implicitly don't trust. And in theory, they could find exploits in any of those devices and run arbitrary code. And this way, if that happens, they're only limited to the devices themselves. As an additional layer of protection, we've written CrossVM from scratch in a programming language called Rust, which gives us strong guarantees about memory safety. We don't rely only on any one of these mitigations in the hopes that both will help keep us secure from any exploits. So I mentioned Concierge briefly in the overview. What it does is, in addition to managing the life cycle of all the VMs, and there could be more than one, users using the VMC command in names other than Penguin could start any number. So we have something that manages them. Additionally, it requires root to start CrossVM, and Chrome doesn't have it. So Chrome talks over dbus to Concierge to start and stop VMs as needed. Additionally, maitre-d or mate-red needs to start the network, and each VM gets its own IP address inside of the Chromebook, and Concierge kind of manages those and tells them, oh, here's your IP address, please set up your network, and gets things going. So one thing, so I mentioned before that when you started a VM with VMC, you're presented with this terminal. Now that isn't over SSH or any other sort of serial device or anything like that. It's using a protocol we made called VSOC shell. Now VSOC, I kind of glossed over this before, but it's one of the para-virtualized devices here that CrossVM implements, and you can kind of think of it as like a really simple SSH with no authentication because it's all local anyways. But yes, we use this to expose a terminal to users over Crosh. So this one is pretty simple as well. I've kind of covered all of the things that this does already, what Mate-Red does. Initializes the network. It tells Concierge over VSOC that things are done and that you can continue to give me more commands. And it executes other miscellaneous things as needed inside of the VM. You can kind of think of it like a remotely controlled init system. We use gRPC in this case to communicate between the two. So I'd say one of the more user visible things about Crostini is the fact that you see all these Linux applications in your drawer. In this case, you've got the terminal and Steam in this particular screenshot. And what exposes these icons is a program called Garcon. Similar to maitre-d, it uses gRPC to communicate with the outside with the host. In this case, it uses it to communicate the icons for the desktop files. For those of you who perhaps are unfamiliar with the internals of how most Linux desktops work, there is a standard for desktop icon or desktop shortcuts and start menu shortcuts, and we subscribe to that. Wherever possible, we try to use standard Linux approaches, standard Linux distribution approaches to things to maximize our compatibility. And Garçon is an important part of that to make sure that users can actually start the applications. It does have an interesting side effect, though, in that sometimes there are applications that are installed as side effects of other applications that you didn't even realize were there. So if I'd actually opened the launcher, you would have seen that it installed Xterm, which is a terrible program to run in Chrome OS. It renders like this big because we have such high DPI, and I wouldn't recommend doing that. But Garçon faithfully sends all applications for users to choose from. So one bit of, I guess this is a kind of a low-level detail that is actually pretty important, but we use Wayland, and Wayland is not a very simple protocol to tunnel between a VM and its host. It doesn't just send bytes over a protocol like most of the other stuff does. It also likes to send file descriptors. This is important because those file descriptors are your things like a frame buffer, things you wouldn't want to send over, 1 byte at a time over a pipe. You'd like to send it as shared memory. And to make this work, we developed an entirely new paravirtualized device based off of the VirtIO family of protocols, and did a lot of trickery to make sure that applications didn't have to change in order to take advantage of this protocol. And so VirtIO Wayland is the device as well as kernel driver part of it. There's also a user space component called SmallEA. What this does is implement a few of those magical tricks that I don't have time to get into right now to make sure that the Wayland protocol works over an entirely new machine. Because that's what it looks like to the guest. The guest, you can think of it as a different machine. It's a virtual machine. How could it share memory with a machine that's different? Again, not a lot of time to get into it, but that was one of the most important details to make sure that we had a performance system. In addition to that, we also really wanted to support X11 applications, which are incompatible with Wayland. There's a few different approaches to how this gets done. We kind of go a more secure yet somewhat hackier approach. I realize that may seem like a contradiction, but basically when you implement X11 on top of Wayland, usually the compositor basically just gives those X11 applications extra privileges that ordinarily Wayland applications don't have. We don't give them those extra privileges, instead tricking all of the applications into thinking they do. And most of the time this works. When you have a well-behaved application that doesn't do a lot, like a text editor or an IDE, it's fine. If the program is trying to take screenshots, it's not going to see anything. If it's trying to implement shortcuts across the entire desktop, you won't see them, unless the window has focus. This is considered a pretty good compromise to keep security while being very usable. I mentioned before the LXC command. That interfaces with LXD, which is sort of the daemon part of it, of the Linux container solution. And this is so that users can choose from other containers if they so choose. We give them a Debian environment with a few extra additions, like Garçon, to make sure that integration is good. But users are free to choose other things. You can point it at an entirely different URL and download an entirely different image. The integration won't be there, but you should have the terminal. And users have already used this to actually take what we've changed in Debian and redone those changes in other distributions, which we're very happy about because we want our users to have as much choice as possible, work in the way that they work best. I mentioned Termina before. For those of you who maybe are a little more familiar with Chrome OS, you know that there's lots of different board names for each different Chromebook. Termina is kind of our board name. That's for our little rootfs that's read-only. And Tattle and Tail are the architecture-specific versions of this. They're read-only, they're verified, they're updated the same way that something like the Flash Player is updated in Chrome OS, and this is so that it doesn't take extra space in our Chrome OS images. So this way, if our users aren't using Crustini, they're not downloading anything extra every time they're updating their Chromebook. But they're still having all the benefits of a verified image that's automatically updated. So I mentioned before that we did some trickery with X11. This leads to some limitations that I think are good compromises. for security. Additionally, there's other compromises. You can't have raw hardware access. Some people asked about this. You can't do layer 2 network access. If you don't know what that is, you probably don't need to worry about the fact that you don't have it. You also don't have KVM access. This is actually kind of a sad one because we're a VM. We should be able to run sub VMs. But as it turns out, there's some security issues with that we haven't ironed out. This is bad for Android Studio. They like to run VMs for their Android emulator. You also don't have access to any of Chrome's data on the host side. This is one of the more important things to protect. I guess the entire last talk was about CryptoHome, all of Chrome's data, protecting that. VMs, like I said, we implicitly don't trust. If we gave them access, we'd sort of been giving them the best part, and we don't want to do that. Additionally, there's a few things that we just don't have implemented yet that we want to, but we don't. Sound doesn't work. USB peripherals will hopefully have. That'll, I think, help artists or people who work on things like Android, or sorry, not Android, Arduinos, so that you could plug in your Arduino and then flash it with some stuff if you're a maker type person. GPU access, that's the part I've been working on lately. Not quite there yet, but hopefully we can give them something that's both secure and fast, so they can maybe run a game or two. And IPv6. Currently being worked on by an intern, our best intern, and we will hopefully have that soon. So extra reading there if you want to read some source code. There's also a giant FAQ section in the bottom there. If you want to figure out more, that's probably where I'd start. I think I'm good there. Any questions? Oh, sorry.
The Dory questions first?
Oh, sorry.
Thanks.
You want me to do Dory questions first?
Yes.
Okay. When can I play Steam games? Well, eventually. Hopefully, eventually. Okay, live question? Was there a live question? All right, I'll do another Dory question. When saying what user target is, how this impact the VM design? So I guess that's a good question. I don't think it affects the VM design so much as it affects what the container looks like. As I said before, we were fine with just dumping users, at least at first, into a terminal, into a bare Debian environment. If we were targeting something like a gamer, we wouldn't have done that. Gamers in general, maybe some of them do, some of them don't really know how to use a terminal. We would have just given them, some kind of app store or something like that. And we wouldn't have worried about so much about the fact that you could choose a different kind of container if you wanted to. Any live questions? Oh. Do I have an extra microphone? Or?
I just had one question about the. I'm assuming that the VM and by proxy the container are both considered unclean, and so you're not giving it any access to data.
That's correct.
Yeah, and one of the use cases was like an Android developer, I assume. Now, is there a mechanism for that user to push data up so it runs on the Chromebook, or you end up having to invent like a secondary communication channel between the two machines?
Sorry, so if I understand the question correctly, you're asking how it is that an Android developer could communicate with the host to run an application or something like that? So today we don't actually allow that for security reasons, but in a dev mode Chromebook, we allow that, I believe, over the IP, basically ADB over IP access. Okay. Let's see if we have another. Do I have more time? Yeah. Okay. So next question: how many Linux applications can be run concurrently? How much memory you got? On a Chromebook like what we've been testing on, that's the Pixelbook, the high-end one with all the memory. We haven't really run into any problems. People who've compiled Chrome, compiled the kernel, Linux kernel, and developed on it. The limit is the same as any other computer. Any live questions that I should go to? Oh, there's one. Where's that extra microphone at? Oh, he's got it.
So I was going to ask, so the manager for the VMs, how many, or I guess how does it handle when you have, say, like 2 or 3 VMs running at the same time? Does it handle that well? Is it
So that's a good question. The way it handles it is it just runs each one of them as a separate cross VM instance. When you try to use the terminal of one of them, you have to give the name of it, and that gets sorted because it remembers when you start the VM what is the name associated with it. If you're asking about how, like when you press an icon, how does it know which VM and which container it does? The answer is Garçon basically keeps a little cookie with each app that it bubbles up, that's saying like, oh, this is kind of the identification. You can think of it like a tuple of the VM name and container name that it uses to start up that application again if it so needs to. Does that answer your question?
Sure. Kind of going off of that real quick, are there any performance implications that you've seen from that? Like if you have more VMs, does performance suffer at all?
No, we pretty low overhead. The only performance issue you might see is that every time it has to start up a VM, if it wasn't already started, you have a delay. It's about 2 or 3 seconds today. We want to get that to like 500 milliseconds, hopefully. We want it to be as seamless as possible.
Thank you.
All right, let me do another Dory. Do Linux applications have access to disk to store any local data if they want? Can they access data for other Linux applications? Can they access Chrome data? So the last question I kind of answered with my last slide. No Chrome data access whatsoever. Can they store local data if they want? Yes. So I mentioned that VM is read-only, but the containers that it starts do have their own mutable disk storage. And it looks just like any other Linux distribution. They can access other Linux applications if they're running inside of the same container, assuming, of course, that you've set up, or the distribution has set up access for applications to talk to each other. So you should see no difference there. Another live question? I think you had your hand up before.
Last question. One last question.
How does the disk space work? Like, do you allocate a certain amount of disk space for the VM? Like, is it reclaimed? And also, same for memory. Like, do you set quotas on how much memory an application can take?
So that is a really good question. So the way memory is apportioned is basically we give 3/4 of the system memory to each VM, which may sound like you can't run a bunch of VMs, but in practice, memory is allocated largely by the host kernel. As long as you aren't actually using more RAM than you have on the system, you'll be fine. If you use more RAM than you have on the system, you'll be less fine. Chrome tabs will start going. Eventually, I guess cross VM. Well, one of your VMs might get killed. As far as disk space goes, it's kind of a similar story. We use a sparse file system format for all the disk images, and so only as users use more data do we actually allocate more blocks to them. If they use more data than they have available, then they're going to find that their disk is no longer writable. If they don't, then they should be fine. Yeah, so we have half of Trim implemented, which is as good as none. If they use less disk space, we've kind of gotten it to the point where they can shrink the disk, but the guest kernel cannot tell the host that it uses less yet. It's one of the things we're working on.
All right, thank you very much, Zach.
Oh, thank you.